welcome to numerical ship and offshore hydrodynamics. Today is the lecture 33. Today we are going to discuss that how we are going to solve the equation of motion, that is the IRF solution, right. Okay. So, and this is the keyword that you have to use to get this lecture. Okay. So, without further delay, let us start. So, this is where actually we are in the last class. So, now I know the solution for A and the solution for beta. So, now again let us go back to the equation of motion again. Now, here we have m plus A infinity. So, I know what is my A infinity now. So, it is x double dash t plus 0 to infinity b tau, then x dot t minus tau into d tau plus c into x equal to f of exciting force. Now, you see in this equation there is lot of things are there, right, and here we only know how to calculate the b tau. Now, we need to now it is a time domain equation. So, finally, you have to solve everything in time domain, right, but here only we know something, it is we required it before even we start the solving the equation of motion, right. So, by now we know how to get this b tau, by now I know how to get this E infinity, right. Now, let us see that what is more required to solve this equation. Let us say give equation number 1, what more is required to solve this equation 1. Of course, I know b tau, of course, I know infinity. Let me again write it little bit, because this I do not integrate till infinity as such. So, frankly speaking, it should be this into x double dot t plus 0 to some tau n, or if we use this the nomenclature that I do in the last class. So, let me use instead of tau n, let us use the tau m, okay, and then it is b tau into x dot t minus tau d tau plus C x equal to f of exciting force. Now, here we know how to get this, we know how to get this, but really still we need to know many more things before actually start solving this equation. What are those parameters? So, one parameter is C and one parameter, very important parameter, which is f of exciting force. Now, today I mean in fact, this all thing is required before we solving this equation of motion. I have to have all this data before we start this solving this equation of motion. Let me call this equation 2. Okay. So, now today let us start with how we can calculate the C, the restoring coefficient first. I do not spend much time on this, because we spend lot of time initially to get the C. Now, you know that for C heave or called the C33, this is nothing but it is rho into G into water plane area, right. So, let us solve, let us think that I solve for C, and then you know that what is the solution for C phi phi, it is nothing but rho G into delta multiplied by GMT. So, in case of GML and in case of C44, it is nothing but rho G delta into GMT. So, we know all these things before, right. So, we really do not discuss on this. So, we do not discuss on how I calculate C33, but we need to discuss how I can calculate my f of t. This is very important. Now, how I get this f of t here, because I have no clue about how to get this exciting force in the right hand side. Now, this also we can get from my frequency domain solution. How? Now, if you solve like a frequency domain solution or let us say Waumit type solution, then you have a data. The data tells you two things. One is that about that each omega, what is the exciting force f of omega, one thing, and also at each omega, what is the value for the phase, or you can say epsilon. These data always there in any kind of frequency domain solver. So, which means that you have omega 1, omega 2 in omega n, and then you can have, now I just make it a small f 1, f 2, okay, it is, let us call omega also, and then f n omega. In fact, just make it the equal nomenclature, call it capital N. Similarly, here also omega 1, omega 2 to omega capital N, we have you can say epsilon 1, epsilon 2 into epsilon capital N, right. So, then f t I know these all are harmonic in nature. So, f t also a sinusoidal function, f t also harmonic. So, I know my f t should be in the form of some amplitude f a multiply by some some kind of forcing function, some trigonometric function. So, it definitely either cos or sin into omega t and plus epsilon, right. So, I know my nature of the solution for the right hand side, does if this exciting force should be in form of some amplitude multiplied by the cos omega t plus epsilon. Now, here we have this this data. Now, here we have some specific data, that means we have again a graph. Now, if you have some kind of idea like how this graph should look like. Now, similarly, if I try to plot, let us say for the heap, my exciting force versus omega, it looks like something like this, let us say, and then let us say the phase. Now, here again this omega, and here you say the epsilon, and if you like a take here it is 0 degree, and then it is positive 180 degree and negative minus 180 degree. So, it should be started with 0, then go up, go down, something like this, let us say. So, this should be the picture for f, this should be the picture for epsilon. Now, you see that many people, everybody has their own way to write this exciting force. Now, what I am teaching you, that is how actually I solve this problem, right. Okay. So, this is so philosophical, like and there is so many ways to do this thing. So, one really cannot say that whatever I am doing is the 100% correct. So, one has to understand this. Okay. If you it's a purely kind of research problem, I would say, and there are many theories developed with respect to this, and of course, all these papers, related paper, related theories, related journal paper, everything will be distributed to you. But as a classroom teaching, we are always going with the very stick with the very basic thing, very simple way of approaching to the solution. Okay. And then let us try to find out at the end the solution I am getting, whether it is really a realistic solution or not. So, in that respect I can guarantee you, like whatever we are doing here, at the end even it is much more simplistic than the proper way, the way the researchers are doing. Engineers can accept. Okay. In the research term, we can say it is within the engineering accuracy. Okay. Okay, so, let us see that how actually we approach over here, because many, there is a many alternative ways, many methods are also available. It is purely a very sophisticated process, and I am doing it with absolutely simplicity. Okay, let us see. Now, what again I am doing over here, the problem is I have a table with omega versus the f, and also this omega versus epsilon, but it is only for specific data omega 1, omega 2, and then it is, let us say, omega n. It is f 1, f 2, and let us say f of n, and it is epsilon 1, epsilon 2, and let us say it is epsilon n. So, this is the data that I am having, but suppose I need to find out in some arbitrary omega. Now, this omega, not necessarily all this list of omega that I am having with me, because when you solve this frequency domain method, you really do not have any such of idea that I am going to do for the IRF analysis also. We are going to use the same omega I that I am using for my frequency domain solution. It is not possible, it is absolutely not possible. So, then here this omega not necessarily fall within this list, but this omega definitely within some interval omega I to omega I plus 1. Now, you understand what I am. So, what we do over here, that we do the simple linear interpolation. Okay. So, that means I know at some omega I, then this is my f of I, and then at omega I plus 1, I know this is my f of I plus 1. So, then at omega, what is my f? This is my that is what I need to do, and I do exactly as a linear interpolation. So, therefore, it is definitely f minus f I plus 1 equal to omega I plus 1 minus omega I, I am sorry, it is the opposite, it is f of I plus 1 minus f of I divided by omega I plus 1 minus omega I multiplied by omega minus omega I. So, this is a simple linear interpolation, right. So, we can get my functional value at that particular omega, which is f of omega, is nothing but, now I can call this again a slope. So, you can call that m of the functional slope f into omega minus omega I plus f of I plus 1. So, this is the formula. With this formula, I can get the solution of f omega. So, now you see, like this is again I say that this is absolutely I cannot say that it is simple, but this is not the only way to do this. Okay. In fact, I would say it is a very simple way of doing it, but again as I said that if I have the sufficiently small omega I, like omega 1, omega 2, omega n, if all are very small interval. So, I have lot of data, like if I take this omega is really, the delta omega is really small, which is some order of 0.001 or so, and then if you plot all this omega, then definitely this will give you quite reasonable answer. And similarly, the phase also with this simple equation I can find out the phase of this phase of epsilon omega also. That is similar way. Again I can do this linear interpolation, I can get it, but sometimes there is a problem. The problem is as follows, like if you look at the phase, the nature of the phase, it might not be very good idea all the time, like it goes somewhere up and then suddenly it go down and then coming up like this. So, the problem is if you here if you have and if you omega is fall in this between, so then really there are some situations like you can have problem. Now, when there is a sudden change of this phase and which is very realistic, sometimes it is going up and suddenly it has shift change, abrupt change, that time this linear interpolation might not work. So, in that is why it is sometimes it is safe that you take epsilon, that let us say if this omega in between this some omega I and some omega I plus so on, it is always better to do this verification that how this your epsilon is changing. So, if this epsilon changing is abrupt, then you have to again you have to decide like whether to go with this phase or whether to go with this phase, right. So, it is it comes with lot of what I said like experience, something like this, right. It is not a is a uniform way of expressing all these things, right. But anyway, in general what you could do is this f omega definitely it is a very continuously changing curve. For this you can have the linear approximation, but while calculating the phase sometimes normally what we are trying to do is you can take the phase at either omega I or we can take the phase as omega I plus 1, you can take any phase if the phase is not that rapidly changing, and when you do the rapidly changing then we have to see that what the other possibilities that we can explore. Okay. But let us forget this part, but in other part that linear interpolation works absolutely fine. Okay. So, now I understand how I get this amplitude f of omega. So, therefore, this f of t of some frequency omega definitely it is this amplitude of this f of omega there which we can get using the linear approximation multiplied by the cos of omega t and then plus this epsilon, or we can call this epsilon I, whatever we can call this f of I, something like this. Now, here there is a problem, not a problem, but thing is that what is happening over here, normally if you look take a plot, then it is a cos term. So, it cos goes like this way. So, now at at t equal to 0, you can experience a very large force over here, and that might cause you some kind of numerical instability. Why? Because at t equal to 0, I really do not want a very large force acting on the vessel. So, then how actually, but again it is here like this. So, then the question should be that how I can write this f. There is a lot of problem writing this, right. Initially I do not know about the phase, there is always some kind of more rigorous analysis required to which phase I should attach with this first. Second one is that how I do the linear interpolation to get this f omega naught. And third now, which is more important and very crucial, that at t equal to 0, when you do this equation, like when you do this m plus a plus 0 to some tau m into b tau cos of omega sorry, it is x dot t minus tau d tau equal to now f t. Now, at t equal to 0, this goes to a very large force. Now, the question is that if this in a very large at starting point, it might cause some kind of a I mean that we are not ready for it, I would say that way. Then how to write it? So, normally we write with the help of some kind of ramp function. Now, what is ramp function? Ramp function is something like, you know, that it is going little bit like this is your ramp function, right. That means, it is of course in a speed breaker. Now, but this speed breaker we always take a continuously this. So, slowly it go up and then go down. We really do not want a speed breaker like this, right. We really want this ramp function. So, what graphically that we really do not start with a very large value. So, what I need this the f, if I call this the force f of t with respect to t, I really do not want to start from this particular point. What I want is it should be here, go up, and then after some time t it reaches the peak P, maybe after the first cycle, because you know this f t is nothing but it is some kind of f omega, this amplitude into cos of omega t plus epsilon. So, this is a harmonic function, right. So, maybe it is periodic, I mean not maybe it is periodic. So, maybe we can the first period we really do not want it. So, I want it after using some ramp function to leads you from here to here. So, how I write this ramp function? So, now remember that ramp functions cannot be for the all the time, it should be acted here and this ramp function should end over here, right. Now, so how to write it, right. So, let us see that how we can write there is again there is a different way of you can write a ramp function. So, let us try one ramp function. So, we just call this R t, some ramp function you can say this half into 1 minus cos of let us say pi into t. Now, let us see what is the behavior of this function R t. So, when we use the t equal to 0, you can say that is this equal to 1. So, then R t goes to 0, right. Now, then when this then when the t equal to let us say 1. So, at that time it is actually going to cos pi, which is minus 1. So, at that time this R t goes to 1. So, therefore, if I use this the ramp function, then I understand this at t equal to 0 it is 0, and then at t equal to 1 second it actually goes to the 1 value. So, if I attach this ramp function with this, so maybe after 1 second I can reach that, but then I really do not want to make it at 1 second. So, I want to make it, I need to devote at least one time period. Now, you know that time period t equal to nothing but 2 pi by omega, right. So, we know that. So, this ramp function I might write in that way. So, R t, if I write this ramp function half into 1 minus cos of, now I can see that pi by time period T p multiplied by the t. Now, if I write this ramp function goes to minus 1 when t equal to time period, right. So, therefore, at least I can at least I can use this ramp function to make my signal beautifully arranged. For the first time period, I am devoting it to set up the force, and then actually we can do this this force continuously. So, you can get a very the nice force. So, this F t I must use with this R t into some f omega into cos of omega t plus epsilon. This should the way to write this ramp function. And I must say this ramp function is this when t is less than equal to T p, and then the value of ramp function R t equal to 1 when t is greater than time period T p. Okay? Fine. So, today let us stop over here. Now, today we discuss how we can write the ramp function, right. So, now this is the ramp function when t is less than equal to T p, and this ramp function goes to 1, right. This ramp function goes to 1 when the t greater than equal to the time period T p. Okay. So, today we are we discuss these things, right, but then still we need to write the equation of motion. Okay. So, so now still we are there, like we first discuss how we can get the beta, how I can get the A infinity. Here we can discuss how we get the exciting force, generate the exciting force. So, now we are ready, and also we discuss how we get the C, the restoring coefficient. Now, we are ready to write the equation of motion. So, in the next class we are going to write the equation of motion, and then if maybe if time permits, we can show you at the MATLAB code the graphs. Okay. So, till then so we stop today at this point. Okay. Thank you.